Okay. For any chemical reaction to occur, and you listen to me carefully. For any reaction to occur, four events must occur simultaneously. And I'm going to give you these four events in just a second to redraw my curve here. Okay. Four events must occur simultaneously, and it turns out these four events occur at the activation energy. These include C, E, N, T. You think I got plenty of acronyms. These four things must come together. You must have a concentration. Now I'm going to give you the words. Effective collisions. Naturally reacting substances or nature. And temperature sufficient to sustain an activation. Now, when we talk about activation energy, it is important that at this point that we understand what the outcomes of studying micro level gas phase behavior is. It gives us insight into why chemical reactions occur, the kinetics and the events that take place. Well, it is determined that these four issues have to occur simultaneously. Otherwise, a reaction is not going to occur. That's why we say activation energy is the magic line. Concentration is what we call an effective kinetic concentration, or just simply kinetic concentration. Now, what does that mean? That means the particles involved in the reaction have to be able to find one another. That's what it means. If you have A plus B going to a product, AB, and you have a container with an A over here and a B over here, not likely they're going to find one another. And so you have poor reaction probability. But if I fill it up with A's and B's, there'll be a greater chance of those particles finding one another. And so you must have an effective kinetic concentration of reactants in order to initiate the reaction. Whether you're at activation energy or not, the particles must be able to find one another. The second issue here is effective collisions. Particle A has to fit with particle B. Now, in one context, if I have A, it looks like this, and B, that's like this. If I orient them to that, then I'll get A and B to combine. They will hook. But what if A and B came together in that orientation. No reaction. It's like putting your hands together. There's no reaction. But if I interlock my fingers, I get a reaction. Like that. So molecules are the same way. You have to have an orientation, an effective collision that will generate an orientation. So at the activation energy, you have so many collisions going on that there's an extremely high probability that some of those particles are going to orient themselves in the proper configuration and lock together, making a bond. So that is the second issue that has to occur. And that's why you push the energy up, so you can get higher numbers of collisions and a higher probability of the particles interacting, forming bonds. Well, there's a lot of math that goes with it, but that's the bottom line. And of course, in the nature, particles must be able to react. Must have naturally reacting particles. And it doesn't take a rocket scientist to understand that one. And some things you pour together and they won't do anything. Some things you pour together and they will do something. Extent of which is part of chemistry. So it's just A plus B, will they react? Yes or no? Well, if you're going to get to a product side, they better. And there are rules and what have you that you'll learn in time why A and B do react and form bonds. And that's all we need to say about that. And T is temperature. Raises internal energy content of reactants to the activation energy point. So if you've got a collection of particles you want to react in a container, they're at temperature 1. Will they react? Well, maybe not. But if you heat them, the energy of the particles goes up, pushes them past the activation energy, and all of a sudden they go through their magic dance and we make products. And so that's the essence of what I'm talking about here. Now, this leads to what we call the transition state theory. And I'm going to boil this down to real simple real quick, and I'll show you the diagrams that go with it. And that's about as far as we can go right now. But there are two thermal designations for chemical reaction, endothermic and exothermic. I know you've heard those. Endothermic reactions means simply that the products wind up at an energy level above the reactants. R for reactant. Whereas in an exothermic, it's opposite of that. Products energy of the products is below reactant energy level. And we can diagram this in the following way. We'll start with the endothermic reaction. Okay, so we're going to say right here is the particle energy of the reactants, or E of reactants. ER is the reactants. Okay? And over here, up here, let me make it a little lower. Energy of the product level. That's where the products are. And so if I draw a line out here like this, then a line here for the reactants. What happens is the reactants go into products. So you're going uphill. But there's one thing that's not shown here, and I'm going to take that little arrow out for right now. In order for you to initiate those products, produce those products, you have to go through an activation energy. That's that magic line I was talking about. And the four events that must come together all at the same time. And when you do, you heat it past the product level, and you go through a little hill, and then it comes down to product side. This is a reactant side. So your reactants are at this level, products are at this level, but what the world is this right here? This distance from here to here, where you start with the internal energy of the reactants, going up to the internal, what we call the activation energy, E sub A, delta E sub A, requires the input of temperature, heat, C-E-N-T, T, actually it should be heat, there. C-E-N-H didn't fit the acronym. Temperature is a byproduct of heat transfer. So we're pushing it up here. Now, the issue is when you push those product reactants up to here, they're now in a downhill roll now. They're not going to roll down any hills unless you get to that activation energy. That's the point. And this diagram is called a transition state diagram. Every chemical reaction has its own personal transition. Some of them have several humps in them. But in order to get to the product side, the temperature has to be, or heat energy has to be applied to the reactants to push it up to the activation energy so they can roll downhill to wherever they're going to wind up. Even though the energy levels are above, the products are above, that's essentially the endothermic definition. But to generate that reaction, the gases have to go up to the reactant level activation energy. Now, an exothermic reaction will show the products below the reaction, but it too has to go through the activation energy. I'll show you. Exo. All this comes out of the kinetic molecular theory, so I'm not just blowing smoke, guys. This is real stuff, man. Okay. So I draw my energy line again. Okay, and so let me put this product. I'm going to make this one product. And here's where we start with the energy of the reactant. And the products will wind up below. But in the process, you have to push that up to the activation energy, and then it'll level off on the product side like that. And so you have this activation energy still to get it up to, this is called the activation point. This is the point at which those four events come together, C-E-N-T. And from the internal energy of the energy of the reactants to That's your delta EA. That's the input of energy, heat energy or temperature, to push it up to the activation area to make everything proceed. So those are the issues that are dominant in the kinetic molecular theory. Particle-particle interactions start out at one energy level and go to another one. That's endothermic-exothermic reaction. Now, everything I'm giving you is qualitative in context. Now, there are a couple of quantitative issues. We gave you one, which is the root mean squared equation, but another one that comes out of the kinetic molecular theory is Graham's law. We have two terms here that we need to be aware of: diffusion and effusion. Diffusion is the random migration of gas phase particles. It's called a Brownian movement. And essentially, it's if you put a drop of food dye in a glass of water and just didn't do any more to it, didn't agitate it, it eventually, the particles would migrate through the entire volume. Same way if I opened a cheeseburger in the front of the room, people in the back of the room would be eventually smelling. But it takes time for the particles to migrate. And this random motion is just that, random. Moves left, right, up, down, and eventually migrates to a final position in the context of where it's going. Okay, that's one definition. Now, effusion is what we want to do problems on. Effusion is the discharge of a gas under pressure through a small opening. For example, if you had a gas cylinder tank that had under pressure, under high pressure, and you punctured it, the gas would escape. Yes? I mean, that's a no-brainer. Okay? Okay. Well, Graham's law defines the velocity of discharge in terms of mole weight of the particles coming out. And essentially, Graham's law states that the velocity of effusion, EFFN, is proportional to 1 over the square root of the number average molecular weight, or just the formula weight of the particles involved. And what it essentially is telling you is that the heavier the particles, the slower they'll come out. So it's an inverse relationship. Now, an empirical equation can be derived out of Graham's law, empirical equation. Well, Graham's law, as I just said, the velocity of effusion is proportional to 1 over the square root of the molecular weight. Now, we can apply the same principles that we used in developing the empirical gas law equations, Boyle's law, Charles' law, and so forth. And I want to equate the velocity of diffusion to the 1 over square root of molecular weight by incorporating a proportionality constant. So I just put a K there. That's molecular weight. Now, solve for the K value, and we have velocity of diffusion times the square root of the molecular weight of the particle under consideration. Now, in this form, problems that you will receive are comparative. Now, what does that mean? That means compare the diffusion rate of CO2 and SO2. Now it comes out as a factor. CO2 equals 2.3 times the diffusion rate of SO2 or something like that, because it's smaller particles. So it works like this. So we're going to compare the two. We know that we'll call this gas 1, gas 2. And so we have V1 on the molecular weight of M1, V2 molecular weight of M2. And so if we let this be particle number 1 and SO2 particle number 2, then we would have velocity of CO2, square root of mole weight of CO2, velocity of SO2, and so forth. Like that. Well, what it gives me is the opportunity to solve one in terms of the other. So I would have velocity of, say, CO2 is equal to the velocity of SO2 onto the square root of mole weight of SO2 over square root of CO2. Or I would have velocity of SO2 to equal the velocity of CO2, and that would be the inverse of this, mole weight of CO2 over the square root of mole weight of SO2, and so forth like that. So if you plug in the values for mole weight and so forth, then you have velocity of SO2 onto the square root of SO2, that's 64 over 44, and you have velocity of CO2 on the reciprocal of that, like that, and I don't remember what the numbers come out. That's 8 over 1.2. So it's 1.2 velocity of SO2 is the CO2. So what that's saying is CO2 will come out if 1.2 times faster than SO2. And it's not dependent on pressure. It's dependent on mole weight, not pressure. Yeah, both of them are assumed to be under the same pressure, same conditions, coming out of the same bottle. So all those little assumptions are kind of given. But the velocity has to be in terms of one or the other, and you can only express this as a multiple factor. And if you did this for velocity of SO2, then that would be the velocity of CO2 times the reciprocal of that. Let me just take this, which would be 0.83, 0.83. So SO2 comes out or effuses or discharges at 0.82 of whatever the velocity of CO2 is. So you see it's a comparative relative to what you solve the Graham law expression in terms of. Yeah, you can use the velocity, root mean square speed in there, but it's still the same outcome. It's a relative relationship. Bigger the particle, slower is going to come out of the system. Now, there is one specific problem out of this, and it's the time of diffusion. Now, Graham's law, the basics of Graham's law is particle comparative. V1 on square root M1, and that's V2 on square root of M2, two particles, just like I showed you just a moment ago. Our physics friends tells us that we can change the velocity number using the equation distance equals velocity times time. And velocity is equal to distance over time. And if we assume that the gas is coming out of the same bottle is transitioning across the same wall, and we just said let the distance be a unity, 1, then velocity is equal to 1 over t. And so what we want to do is substitute it for the velocity numbers in the expression. That's all we're doing. So if I have a V1, I'll have a 1 over T1. So then our equation now becomes square root of M1 over T1 to be square root of M2 over T2. So it's an inverse relationship to begin with. The bigger the particle, the slower it's coming out, the longer it's going to take. The smaller the particle, the less time it's going to take. Okay, so you can go with that. Okay. If argon gas diffuses at 25 seconds, what is the time of diffusion for helium gas? Same kind of idea. You just plug and chug, okay? You calculate formula weights, and you're given the time of 1, you solve the third value. That's all it is. So it's pretty straightforward in terms of the equation you're using. Now this will give you a number outcome. So if we let M1 be the argon, square root of M argon, that's the time of argon diffusion, square root of helium over time of helium diffusion. So argon is what? 40. So we have square root of 40 over 25 seconds. And square root of helium over unknown. And that way. So solving for the time of diffusion for helium, not hydrogen, helium. Okay, so that'd be 25 square root of 4 over square root of 40, and it all comes out in seconds. That's exactly what you got to do on exam day. You'll have one of those. Right. I get about 7.9 seconds. And say 8 seconds. Something like that. Does that make sense? Relative to the mass of the particle. Well, it should, because argon being 40 atomic mass units against 4 atomic mass units for helium. Helium would scoot out a lot faster and in less time. That's what bottom line. Okay, say, what's the RMS velocity for water vapor given H2O gas at 300 degrees Celsius, 273, 573 Kelvin. Okay, and 3 and okay, what you need to remember here is simply RMS velocity is 158 square root T over the mole weight, and that all comes out in meters per second. When you plug in the numbers, 158 and 573 Kelvin, don't worry about units now. This comes out in meters per second. If you want to see the derivation, go into the Ebbing text, and that's the same chapter in the kinetic molecular theory section, and they work it out for you. But we don't have time to deal with that. Mole weight of water is 18, and it all comes out in meters per second. And I got 891 on that. So it's a real simple calculation, guys. Just learn the formula, plug and chug, and you got it made. Now, if you're doing research on gas phase kinetics, then this might be useful in talking about activation, and we'll learn about that in Chem 2. The nitrogen diffuses through a pinhole in 84 seconds. So the time for N2 gas is 84 seconds. While it takes an unknown gas 32 seconds. What's the molecular mass of the unknown gas? Is the question. Well, the molecular mass of N2, 28 atomic mass units. So they're going to cancel out anyway. Okay. So we know that square root of M1 over T1 equals the square root of M2 over T2. And who do you apply this? We can call the first one N2 and then the second one unknown. Solve for T2, the unknown, and that's T1 square root of M2 over square root of M1, plug and chug. So that's 84 square root of, that's a time, isn't it? I'm putting ratios, sorry guys. Come on. Sorry about that. That's unknown. So we need to get the mole weight of the unknown. That's this one. So that would be square root of M2, which is the unknown. That's square root of M1 on the ratio of T2 over T1. And so, based on the data, M1 is 28 and times 2, 32 over 28. And so that's the square root of that. So you're going to have to square both sides when you finish. 28 square root times 32 equals, divided by 28 equals 6.05. Now that is the square root of M2. So square both sides of that. I get 36.6. Number 2 was 84. That's right. Yeah. 84 over 28. Thank you. Going too fast. It was 3, okay. Okay, so that's 3 times whatever that is. It's 28 square root times 3, so 15.9. Square that. It looks like 252. So it's just a matter of working with the empirical relationship. You give them 3 solves here, and I'm assuming now they'll handle that.